In this video, we're going to review the R code made available for Module 3.4 that addresses the LSC curve fitting model. If you'll notice that this particular folder has several test programs, and we'll work our way quickly through several of them. And so again, if we just double click on the RPROJ file, it will load the way it was previously left. And I'm going to run through the regression test program, the LSC curve fitting test, the LSC regression independent variables, and then a coefficient sensitivity. And so quickly, let's work our way through the regression test. This is mainly just to illustrate how the LSC model actually functions. And so if I have there's a set of data in a DAT file, the regression input data file. Let's see where to go. There it is, the regression input data.dat. If I read that data file in, I can examine what exactly is it. Well, these are a handful of yields, as well as the slope coefficient parameters x1 and the curvature parameters x2 without much commentary. That's just the data that is made available. I could print it to the console if I wanted to be sure. The way you run a linear model in R, there's a whole bunch of different ways to do this, but from the stats program, basically LM stands for linear model. Basically the Y variable, the formula is going to be the LSC data using the variable Y, and then I'm going to regress it on X1 and X2. If I run that at a LSC, I return the results of that into this variable called LSC. It contains an enormous amount of material, as we can see in the environment. It's very difficult to disentangle. I can just summarize it by looking at the estimated parameters, standard error, and a host of other interesting statistics. The R squared is 0.992, or the adjusted R squared is 0.9893. And so I can look at a host of things, but my primary interest is in the coefficients themselves. And so the intercept, which would be the level, is 4.33. The slope is 4.159, which is negative, which means it's an upward sloping curve, and I have a negative curvature fit. And so I can look at the fitted parameters and then examine the residuals. These residuals are fairly small. And so my interest, however, is in capturing the what I refer to as the beta coefficients in this linear regression. And I can just produce them in a vector called betas. 4.33 is the intercept, and we have x1 and x2. If I wanted to examine what this looks like in a plot, I could run, I could set betas 1, 2, and 3 to level, slope, and curvature, and then run this particular plot and see what it looks like. In this case, making it a little bit bigger, line 53. If I just run it again, it gives me the illustration of a regression. That's the Y1 variable. If I add the Y2 variable and then add a legend, the fitted curve is the triangles. The actual curve is the circles. And so what we observe is this nonlinear variable, whatever it is fit very well with the LSC model using the LM function. And so the next thing to look at is how do we actually examine the LSC model applied to interest rates. Again, you'll see the advantage of having these commands at the top. If I want to run a second test program, but I don't want to get tripped up with these variables, I basically can, I can take out the trash, so to speak, and clean up the environment, and I'm back to where I started from, and I can just highlight this whole program and run it. What does this program do? I should have made this bigger, and so if I make this bigger, run it again, what this does is it fits several U.S. Treasury curves, and I'm just going to quickly run through them. And the thing to observe is that the LSC model fits interest rate data extremely well. And so for different days over a long history, the LSC model has a extremely good fit. And so how do we get this to generate so many different plots? We'll look at that in just a minute, getting all the way back to 1989. And you can see just running through it that the LSC model fits a variety of different shapes of the term structure, and it fits it very well. And so let's look at this code in detail. And so once we get past the taking out the trash, so to speak, we're going to assume a three-factor model. How many scalars do we need? Well, we only need one because the scalar applied to slope and curvature 1 are the same. We're going to set the scalar equal to 2.0 and then number of dates. And so I could read in number of maturities. I could read in some LSC data and take a look at what it is in case I don't remember. And this is a set of interest rate data. And what you'll notice is sometimes the data is not available, but that's not a problem. And so we can look at the number of dates, look at just print out the first 10 lines to make sure we understand what it looks like. I can fit the maturities into the first observation, and then if the data source is interest rate swaps, then I have a ninth variable. And again, I can just capture the dates, review the data that I have. And so I have a set of different maturities. I've inputted the various rates, can examine the dates that are involved, what the maturities are. I could put this in a matrix and then insert the rates. And so now I have it all in a nice format, a single matrix. And I can have the factors in a set of, and also in a matrix. And then I can basically load up those factors based on the LSC X variable, the LSC model's X variable. And I can create level slope curvature in R squared. I can create a loop of number of dates. And so if the number of dates that I have in this particular package is 35 dates. And so if I run through this quickly, it will have produced the 30th rate. If I look at the intercept, slope, curvature, the fitted rates, I can estimate what the fitted rates are by using the appropriate maturity and the intercept, slope, and curvatures that were found in the LSC model. And so now I have the rates and the fitted rates, and we're able to compare them. We'll compare them by plots, and I'll loop over all the dates, and that's how I produced all these different plots. And so I'd encourage you to spend some time with the LSC curve fitting test routine just to get familiar with the kind of data that the LSC model fits and how it fits the data very well. This next test program, it looks at independent variables test. And again, I recommend before you dive into trying to understand what the code does, just run the entire package. If you run the package, then you can see this is the different weightings applied to the different scalars applied to the three-factor model that we looked at in part 2. And prior to that, we looked at a five-factor model, four-factor model, three-factor, two-factor, one-factor. And so what this program does is it just illustrates the regression independent variables from a 1-factor model, 2-factor model, 3-factor, 4, 5, and then it applies the different scalars to a 3-factor model just to get increasingly acclimated to what this model does and how it's applied. The last test program is how sensitive are the coefficients to changing the parameters, level, slope, and curvature. If I just run the entire program, again, we looked at this before. This is the R code that produces these charts illustrating the effect of slope, the effect of curvature, the effect of having an upward sloping curve with different curvatures. And so again, I would recommend that you spend some time working through this code. I have personally found the LSC model to be extremely useful in a host of different issues, primarily because it's easy to interpret and you can trade. Once you get results, you understand the variables to trade if you believe you have too much slope risk or level risk, all of which we'll get into in more detail when we get into the different risk management sections of this book.